Okay, welcome everyone to my continuation of what is algebraic graph theory. So I would like to wrap up the kind of the sub part of this lecture series, whatever you want to call it, video series on YouTube, about random graphs, which I enjoyed a lot. So I enjoy random graphs a lot. I hope you enjoyed it as well. Anyway, I want to wrap it up by two very similar looking kind of patterns, where one of them is easily provable and the other one is really difficult. It's a very strange dynamics between the two. They're kind of very similar, but then somehow still very different in the type of statements you will get out of it. So for the second one, which is the next one, I show you the nice one first, and then I show you the difficult one. So the nice one is about cliques, and the difficult one is about colorings, which is kind of the same. I'm going to that in the next video. Right now, I only focus on cliques, where we get an extremely beautiful statement. It's extremely fantastic. And then I'm kind of doing the same for the coloring. And the pattern looks exactly the same, but we get a much weaker statement because somewhat is kind of different a little bit, and the proofs need to be adjusted, but that's very difficult, and it somehow doesn't work. And I kind of like that interplay between two kind of very similar notions that have the obvious similar patterns, but then it's kind of really impossible for one of them to prove what you want to prove, and for the other one, it's really easy. And as I said, we go with the easy one first, because I don't know, always do the easy one first, I guess. And it's about peaks, so we will see what it means. The other one, the difficult one, is also about peaks, but you somehow can't prove that. It's kind of a very fun thing. But anyway, so what is a clique? It's essentially a complete subgraph of your graph. So here's a graph, whatever it is, and it has a certain number of cliques. And the clique is just kind of these two guys form a clique because they are kind of maximally connected, and there's nothing else you can do to fill them in. These three guys form a little bit of a bigger clique because, again, they are all connected, but now it's a bigger one, so you could fill in a surface here, just an area. This one here is even the bigger one, so there are four of them, and now you can really fill in an area. So I would like to think of the various forms of cliques. So a one clique is just a vertex, a two clique is just two vertices with an edge, a three clique is something where you could fill in an area, a four clique, sorry, an area, and that was right, that was actually right, where you could fill in an area. A four clique is something where you could fill in a volume. A five clique is where you be able to fill in the next level of volume, and so forth. And we call a clique maximal if it can't be increased. So this vertex itself forms a one clique, but it's clearly contained in a bigger clique. And the maximal one where it is contained in is this one, which forms the volume. Okay, I hope that's reasonably clear. So just a vertex cliques are kind of maximally connected as maximally complete subgraphs, right? So complete subgraphs, everything is connected to everything. And we are asking for the maximal ones, like in the picture above, right? So the picture above, really what is illustrated are the maximal cliques. And you can see that by vertices, they're just zero-dimensional, and then a pair of them has an edge, it's one-dimensional. A triple of them has an area, it's two-dimensional. Whatever the next one is, a four tuple has a volume, it's three-dimensional, and so on. And we are asking to find the clique number, the size of a maximal clique. So in this case, the clique number would be 4 because we have either this one here or this one here. So both of them contribute clique number 4. So essentially, the question is, what is the biggest simplex you could put into your graph, such that all vertices along the simplex are connected? And that's a clique number, which is fairly easy to compute. So a bit surprising. So, and I want to do that for random graphs. So what did I do? I just put it in a machine and ask what's happened. So I used the machine to create 10,000 random graphs. In our usual notation here, these are the coin flip graphs. On 50 is the one above here, 50, and on 100 vertices. Okay, so the 101 is this one. A coin flip graph where you literally have probability 1/2 for drawing an edge between two vertices. Okay, I did that, and it's kind of, the pattern is kind of completely obvious. and has really a concentration. So in the first case, the clique number is either 7 or 8, and there are a few fluctuations just because I have, well, you always have fluctuations in the setting, right? But you can ignore 6, 9, and 10, essentially. In the second case, essentially everything is, a clique number is 9 or 10, and then some really, really tiny fluctuations. So just using this very, very simple calculation, you can actually show or kind of convince yourself, it's not really proof, you convince yourself that there's a concentration of the clique number around 1 or 2 values. It's not quite clear whether it's 1 or 2. The first one might be a little bit smallish, so maybe that's why it looks like 2. The second one, it's not quite clear. So what do you do if you're not quite sure if it's 1 or 2? Well, you go 1 up. So here is 200, and now it's literally clear that it's concentrated along 1 value. It's really a peak. There's a peak of the clique number of those graphs, which is kind of very exciting, right? So it's kind of, okay, in a random graph, could be kind of randomly connected edges. So why should there be some nice concentration of something like the maximally complete subgraphs? But there is. It's clear from this pattern. You can essentially ignore everything, and there's some number around 11. And the only thing you need to do, if you would like to prove that yourself, leaving the fact aside that you need to prove it, is you would need to kind of get a good idea what the formula would be, connecting 211 in this case, and maybe 109, or maybe 9 point something, because you still have a spread here. But that's not so difficult, and I'll show you the answer in a second. But I hope it's kind of clear that these computer calculations already suggest that there should be a peak of the clique number at a certain value. And indeed, you can show that. The formal statement is a bit annoying. I've written it down here, but essentially it says that the clique number peaks at 1 or 2 values, depending a little bit on n and p. So here I even have a general p. So, but you can think of it as being just essentially the clique number is this number, 2 times log 1 over p of n, which is just a very explicit formula. And this number will end somewhere, and then you just essentially go to the next integer. That's essentially what you do. And here's kind of the formal statement in case you really want to read that. But essentially, there's a function which is a bit ugly, but anyway, not so difficult. And everything is concentrated along the function plus or minus epsilon, which then depends a little bit on n and p, whether you actually have 2 integers or 1 integer in that spread. But usually you only have 1 integer. In particular, for n to infinity, there will only be 1 integer. So I kind of ignore the small case, and I just can say everything is concentrated for large n around this number, which is kind of a fun statement. So where the number pops up from, it essentially comes from the proof when you just think about what the kind of the spread of the edges does. Anyway, I think it's a fun statement. So the clique number of a random graph is really easy to compute, because if n is large, you can just have an explicit formula, 2 log something blah blah. It's a very simple formula, just using log itself. It's kind of a fun statement, and it's beautiful because it really just gives the staircase functions. So here is the clique number, and this is the number of vertices, and I of course again use p of 1 over 2 because it's the most exciting value, I guess. And you can clearly see that the clique number, up to some low number fluctuations, which I'm ignoring, is completely constant on a certain slice that gets longer and longer on this staircase size. Constant in the sense that almost all graphs have this clique number. And yeah, there's only 1 peak if n is large enough, and it kind of has this funny staircase pattern, which is kind of a really, really beautiful statement, I think. Anyway, next time I will show you exactly the same pattern for the coloring, but then you can't prove that, which is kind of very annoying. But anyway, we'll see that next time. I hope you enjoyed this video, and I also hope to see you next time.